7.2, another way to solve a triangle. This happens for a non-right triangle. And what is different here between the law of sines and the law of cosines, is that we are dealing with knowing two of the three sides with an angle and trying to find an unknown side. Or if we happen to know all three sides, we can use this to work backwards to find the missing angle. So it involves three sides and an angle. For the law of sines, that was always a pairing with an angle measure and its side length. And so it was two angles and two sides instead. So it's really just a matter of what is given. This is the important information here at the top. Three different variations of the law of cosines. And if you look at the last one, it looks an awful lot like the Pythagorean theorem. C squared equals a squared plus b squared. It's just the adjustment that we have to make at the other end. So this visual over here on the left is for the proof. If we set this up in standard form, where one of the vertices is at the origin and the other one is on the horizontal axis, that lets us put in a bunch of zeros for the coordinates. Drawing in the height y, that's the altitude there. I can identify from the little triangle on the left, if I call that C, what the coordinates would be at angle B and at angle C. And then I had this picture because it's just an awful lot of algebra for you. So using the distance formula to find the side length. And then it requires squaring both sides, a little bit of substitution, and then foiling when it says square the two expressions. That's really foiling these two up here in the third line. And then we clean it up a little bit just by rearranging, do some factoring, and use this, which we didn't spend a whole lot of time on, this fact that sine squared A plus cosine squared A is equal to 1. So in class, we typically do this just for a little bit of algebraic practice. You really just need to know what the law of cosines is, and then it's a matter of working through my triangle. So if we look at these examples here where we're just solving each triangle, we'll take a look at number 10. So angle A is, or I'm sorry, side A, little a is 10, B is 3, and angle C is 15. So maybe not drawn to scale here, but if I draw a triangle, I'm going to put angle A here, and then side A is at 10 units. If this is angle B, then this would be my little b over here, which is 3 units. And then I'm left with angle C, which I know is 15 degrees, and I'm trying to find side C. That's supposed to be a lowercase c, and the angle is the uppercase C. So what I have here that we talked about with the law of sines really is a side angle side. My 3 and my 10 meet at angle C, which is 15 degrees. So that's my side angle side. If I have these two sides, I can find my missing side, C. So C squared equals a squared plus b squared. That's Pythagorean theorem. It's always minus 2 of those two sides. So if it's a squared plus b squared, you repeat the a and b there, and then it's cosine of the angle, and the angle here at the end matches the side at the beginning. So if this is side C, that has to be angle C at the end, and then again the a's and b's are what repeat. So I don't know what C is. C squared is equal to 10 squared plus 3 squared minus 2 times 10 times 3 times the cosine of 15 degrees. Now that is an awful lot, but we can put all of that in a calculator, and if you do, you should get that C squared is 51.044. So to find C, I have to square root both sides, and so C is equal to 7 this says to the nearest tenth, so it's 7.145, so it becomes 7.1 for side C. So now that I know side C and I need to find my missing angles, I actually hop back to the law of sines because I have C's paired together. So I know that the sine of 15 degrees corresponds with my 7.1, and then I can figure out one of my other angles, say the sine of angle A divided by side A, which is 10, or I could have done the sine of B over 3, because I know that that's the length. So I have to cross multiply. 10 gets multiplied by the sine of 15. And then I'm going to have to leave that 7.1 equal to the sine of A. So A is actually the sine inverse of whatever that value is. So 10 times the sine of 15 degrees divided by 7.1 should give me an angle of 159 degrees, which is a pretty big one. If I look at my 159 up here left, I don't have a whole lot of space left for B, which makes sense as that's going to be a rather small side. Granted, my triangle is not at all drawn to scale. It really should look more like, not like that. It should look probably more like this, with A here at 159 degrees. And then my 15 degrees at C and B. If I want to find angle B and I'm just missing that, then 180 minus the sum of 159 and 15, which is 174, that only leaves me with 6 degrees for angle B. So the law of cosines allowed me to find side C. And then once I had side C, because I was looking for an angle measure, I needed to move to the law of sines. And that lets me find one of them. If I wanted to do the law of sines again, I could, but otherwise I can just use the triangle sum theorem to figure out that angle B is 6 degrees. So it is an awful lot of work to complete the triangle, but remember, typically we're just finding one missing part, not every single thing that's missing. Just like with the law of sines, and this should be a breather after what we just went through, there's a formula for area. So the area of a triangle with those 3 particular sides is this area formula here, where S is the semi-perimeter. So that's half of the perimeter, which is the sum of all of those side lengths. So if we try something like number 26, actually let's do number 28, just because it has 3 distinct measures. 16, 10, and 8. So the perimeter for 28, 16 plus 10 plus 8 is 34. And so my semi-perimeter is going to be 17, half of 34. So 34 divided by 2 is 17. And then my area is simply the square root of 17. And you could work these out in your head, but 17 minus 16, so times 1. And then times 7, 17 minus 10, and then multiplied by 9 to get the final one. Remember, it has to be the square root of the entire thing, and it says to round to the nearest square unit, which should give us 33 meters squared. So the area formula, again, just an easier substitution, and it's when I have all 3 of those lengths that I can find the perimeter, cut it in half to get the semi-perimeter, and then use this Heron's formula to find the area.